Our next couple problems involve finding area under a curve. We're looking at the integral from 1 to 4 of the function 3 dx. So we want to think about these next three integrals geometrically instead of as a limit of a sum. So our function that we're looking at is y equals 3, and let's sketch that graph. Y equals 3 looks like horizontal line, and our limits of integration are from 1 to 4. So here we have 1 to 4, and we're interested in finding this area of this shape. Since this is a shape we can find an area of geometrically, we can go directly to the solution here. This is a rectangle with a base of 3 and a height of 3, so the area is 9. And that's a lot shorter than the limit of the sum. Let's look at the next one. Next one, the function is a line with slope 1 and intercept -1. So here's our intercept. Here's our line. And we're going from 0 to 3. And what we saw from one of the previous problems is that when we take the integral, the definite integral, we end up with the net area. So this underneath the x-axis will contribute a negative amount, and this above the x-axis will contribute a positive amount. If we look at the shapes, we see a triangle here and a triangle there. So our area, or net area, is the opposite of 1/2 base times height for the small rectangle, and then a positive 1/2 base times a height for the larger triangle, giving us -1/2 plus 1 equals positive 1/2. Oh, just kidding. 2 positive 3/2. There we go. I can add. Okay, so triangles there, rectangle in the previous one. This one would have, again, been longer using the limit of the sum, but we could have done it because we would have resulted in just some i's and some numbers that we're adding up at the end. This next one, we have y is equal to the square root of 1 minus x squared, and we want to sketch that. Well, if I were to square both sides, we have this, and getting the x and the y on the same side, we recognize this as the equation of a circle. That is, it is actually just the top half of a circle, because this is just the positive half of our circle with the radius of 1. So we're looking at the area under this curve. That is the area of, looks like 1/4 of a circle. So we can use the formula for area of a circle, pi r squared, but we only want 1/4 of it. So our solution is pi over 4. Now this one would be impossible to do with the limit of the sum, because we would end up with the square roots of some things to do with i's, and we don't have formulas for square roots of something with i's. So geometrically, at this point, we have to recognize this as a part of a circle and interpret the area geometrically.